Welcome to Lecture 10. Today we're talking about trees. Some people are worried about not getting participation points because their internet or their power is out. If your power is out, you have more things to worry about than participation points. Just send me an email and we don't won't dock you, right? So again, if you are out of power or you are otherwise having a one-off situation where you can't make it, it's okay to just send me an email and we'll figure it out from there. I will not dock you because your power is out for participation points. All right. Okay. So let's go ahead and talk about lecture 10. Today we're going to be talking about trees. And the thing that you should know is that up until now, like when we were on topics in this class, we've been talking a lot about lists and arrays and stuff, right? We've been talking a lot about linear data structures. So up until now, we've been talking about data structures that kind of look like this, right? They're a single row of items and there's cells in that row, and you can really only go left or right and go from there, right? And there wasn't really much directionality to worry about apart from going left or right, right? We had an array. It wasn't so much too scary. It was a data structure that everyone's hopefully seen before. We had a list, same thing, right? And that's what we were talking about before the exam. Now that we're after the exam, we're going to start talking about other different types of data structures that give us more choice when it comes to traversal. We're going to be looking at data structures that give us options, right? So the idea here is that we're going to have hierarchy. Instead of having a linear data structure, we might have a data structure that is more and more hierarchical. So something that has levels or layers or some sort of ordering that's not just flat and going only left or right, but we have options, right? We have options at every turn. So thematically, we're going to start that by talking about trees. Before we do, let's go ahead and talk about announcements. Homework 3 came out and there's some hiccups on it. There's some typos and some issues, and that I apologize for that. We fixed all the major typos, but you should watch the video here on Piazza in case you have any questions or concerns. So there's a 15 or 16-minute video linked in the first post on Piazza, which talks about how to get started on the homework, right? So if you are unsure about how homework 3 gets started, like how you want to work on homework 3, which is here, please watch that video. And please also check that you have the right pseudocode. The right pseudocode looks like this, right? So there's no, it should just say here for each element, EL and list, and it shouldn't say starting at index 1. And there should also be a return middle.get of 0 here. That was, both of those were typos that existed in the code previously. I have fixed them in every repo, but you might still have to pull on your applet, especially if you got a copy of it last weekend or on Monday. And I apologize for all the difficulties. This is a brand new homework. We had some typos coming out and I apologize, right? Everyone makes mistakes. But the most important thing is that if you have any questions, please ask on Piazza. You can see that a lot of people have already been asking on Piazza. You might not see it as much since you have the public view, but I see a bunch of questions on Piazza, and you can see that some of them are on homework 3. Please do, if you have any questions, ask, because it's probably my fault, not yours, and we can help you debug whatever it is that we're currently stuck on, okay? Homework 0 feedback should have all been emailed out to your GSU email addresses. I believe I sent them to every single person that had a valid Gmail or GSU email address. If you didn't receive an email or a grade, please make a private Piazza post at this point and we can debug and help you out. Chances are we just missed something and we can fix it. But if you see anything strange, make a private Piazza post. We'll be here to help. Now, these grades should be like your final grade before corrections and also before me looking through all of the suspicious activity, trying to make sure that no one was taking shortcuts, no one was cheating with respect to homework 0, right? As I said before, all of the homeworks, we're just going to release the grades as we have them, and academic dishonesty checks are happening in the background. I'm having conversations with Chegg and some other places to make sure that if you did copy off of a website or you made a post on Chegg, that I will find you and you will get a 0, right? But for now, you have points. Later, you're going to have a kind of a serious conversation with me, right? I'm not, there's no getting around that. But if you want to tell me in advance that you cut corners or you otherwise were being academically dishonest, please send me an email. All right. Okay, so if you haven't already, please read the homework 6 announcements. I'm going to actually make another post later today, but these announcements tell you about all of the most important things. So how homework 3 is released, how quiz 4 is this week, how you shouldn't talk about the exam until Thursday of this week, the deadline pushes for the homework corrections, and how we're going to make sure that exams are fair and less stressful in terms of time, right? Um, it's really important to me that y'all feel good about the exam, that you don't feel like your soul was crushed. So I'm taking all the feedback that you gave that there wasn't enough time to answer all the questions, and I'm thinking carefully about how this week's, or sorry, not next week, but next exam, how it will be structured. Right? How do people feel coming out of now that you've had a few days after exam one? Are you still like feeling the same things you felt that night, or you feel like it feels different for you? I'm just curious. Okay, some people still feel a little bit soul crushed. That's fair. Still scared. Okay. It's hard, but nothing insane. All right. Remember, please just give us the time to grade. All of our TAs are going to start grading today. We're going to work really hard to get the grades out soon. And then if, again, everyone didn't do well, if everyone like did really poorly, then I will give the entire class a boost, right? But like, try not to worry too much right now. I know it's stressful. I know it's hard not knowing something like this because it's super important, but we promise we'll get the grades out as soon as we can. And we're working hard this week on getting caught up on all the grades, not just the exam, right? In general, you should be keeping track of the week's announcements in order to be successful in the class. So check that out if you haven't already. Did I just post the link in Piazza? Yes, I did. Cool. I posted Piazza link in chat. Cool. So today we're talking about an intro to trees. We're going to go over the definition. We're going to talk about some properties, and we're going to look at some examples in Java. Then we're going to look at two algorithms on trees, so sum tree and max of tree. And then we're going to talk about traversals, in other words, ways to print out certain items in the tree. Um, we're going to start by talking about the definition of a tree. And a tree is defined right now essentially as a hierarchical data structure that has some value and some children. Every child is also a tree, making this data structure recursive in nature. So in other words, you can look at this tree, you can see that there's some circles. These are the nodes. Each node has a value inside. So in this case, it's a node filled with numbers. Each node has a number inside. And we have some arrows pointing to some other nodes. So you can see how this is a hierarchy. This is a way of showing data in a way that's not just flat or going from left to right, as we saw in previous lectures. In this class, there will be no such thing as a null tree. Some of you might already think you understand trees, and one thing that I need to let you know that's super important is that you shouldn't confuse this with a binary tree, which has at most 2 children, or a binary search tree, which has some other properties where the left child is smaller, the right child is bigger, recursively, so on and so forth. We do have no binary trees, but we're not talking about binary trees this lecture. We're talking about trees. You can see this tree, for example, has 3 children here, 3 nodes sticking out of this node with 7 in it, and therefore it's not a binary tree. We'll cover binary trees and BSTs next lecture. All right. So the first question we should ask is, why do we even care about trees? Like, what's the point of studying another type of data structure? Why don't we just hold everything in arrays? Well, it turns out trees are used everywhere. The way that they structure data is actually really powerful. They allow us, for example, to build heaps, which is, a form of a tree. You have a phone, and whenever you type something in a phone, the computer inside tries to give you suggestions on what you want to type next. It has some form of autocomplete based on what you've typed previously, and that uses the tree data structure. In fact, homework 4 is going to be about building a basic version of autocomplete in your phone. Whenever you type something in, it'll give you a list of suggestions on what you meant to type, which is going to be really cool, and I'm excited for that. Databases. So anytime you use a website and that website has data that it's storing in a database, we're actually messing with trees in the background. Trees turn out to be a really effective way to store information, to quickly retrieve information. And so that's a fundamental thing we want from our databases, right? To be able to find something fast and to put something in the database quickly. Games, anytime you have a artificial intelligence in a game like chess or Fortnite or any other game with any sort of bot, you can think of the bot's movements dictated by a game tree, which models the set of decisions that the bot has to make and how to make the best one at each stage, right? Programming languages. So like if you work in Java or in any other programming language, when you compile, there's a program called the compiler that actually interprets your code. And the way it starts is by creating an abstract syntax tree. It looks at your code and it structures it in the format of a tree. It dissects your code and splits it apart and analyzes it as a tree, a parse tree. Yeah, exactly. And similarly, many web technologies use trees in the background. Like for example, when you download a web page and show it, like for example, this page here or this page here, all of the information on that page is stored in a tree and sent across the internet through HTML or XML or JSON. And all of those things are fundamentally tree-like structures in your computer, right? Um, we already mentioned this before, but we'll see in the following lectures how specialized forms of trees actually provide fast ways of searching. We'll see binary search trees. We'll see self-balancing trees. Those are things that you'll pay attention to in the next lectures. All right, so let's go ahead and take a look at all the vocab we care about. So hopefully this is review for most of you, but we're going to look at all of the different words on this list and try to understand them one step at a time. I encourage you to take notes and write them down for yourself and use your own words. Um, I'm going to use this vocabulary for the rest of the semester, so you will need to know all of these terms. And so we'll need you to feel good about all these terms and write them down for yourself. Obviously, this is not just like a list of terms. This is instead a diagram with labels, which is why you'll need to write this on your own. Okay, so let's start with the first term. Let's start with the idea of a root. So a root is just the node or the tree with which, like, it houses all the other elements, right? So a root node, this, let me just make that clear. A node is a circle, right? Is one of the circles, and it has a value and children, right? So in other words, all nodes are trees and all trees are nodes, right? You can use them interchangeably right now, where when I say a node, I really mean a tree. And sometimes I'll say tree node to make it very clear, because later on we'll see different other kinds of nodes as well. But the root node, which is this thing that this term that I've squared in red here, is the first node in the tree, or the node that holds all the other nodes, right? So it has some children in here and here, and then it has some grandchildren here, and it has some great grandchildren. All of these are connected together through these orange lines called edges or branches, right? Hopefully this again is familiar. These just show the relationships between two trees. A tree can have other trees inside. So for example, this tree here has a child here, which we'll call X, and a child here that we've called Y. And children, again, are just other trees that are smaller and within the big tree here. Right? So we can have a parent-child relationship. For example, X can have child 1 and child 2 here. And X is a parent of these two nodes down here, but it is a child of the root node. Likewise, Y can have child 3 here, but it is also a child of the root node as well, which hopefully, again, isn't too scary, right? So children nodes and parent nodes are all just nodes that have relationships relative to each other. We also have this idea of siblings. So for example, we can have A here, we can have B, we can have C, which are all subtrees. Sorry, not subtrees, but siblings. So B in this case, and A and C they all have the same parent in this node here, which I've called 1. They all have the same parent, and therefore they're all siblings. And another thing you should know is this idea of a leaf node. So a leaf is essentially a childless node, right? A tree without any children. So we can put this as node Z here. It has no children. Since we're not using the null tree, roots must have at least one child, and there must be a root. So in the case of the root node, if we don't have a null tree, then we can have just like a node without any children. For example, this is a node without any children, and that would be the root node. Another, let's see, question someone asked. It's a good question. Did I say it has children? Okay. Yeah, so you can have no children, and that's fine. So I said, yes, you need to have a value in children, but some trees don't have children, and that's perfectly okay. A node is a leaf node if it has no children. That's correct. Let me just type that here. Has no children. And I'll post maybe a vocab sheet or a summary of all of this information on our website so that you can do some reading here, because I know that this can be a little bit overwhelming. I'll post the basic vocab on the website so that you can review it. But essentially, a leaf node is a tree or a node that has no children. How many leaf nodes do we have here? I'll give you all 10 seconds to think about it. Which of these, based on the labels that I've given all of these nodes, are leaf nodes? Okay, so most people are saying 5. I don't know why some people are saying 25, but there are at least 5 nodes that don't have children, so there are 5 leaves. So we have this one here. Let me do another label so that it's easier to see. We have this original one here that we said was a leaf node. We know that this one here is a leaf node because it has no children. And these siblings here also are leaf nodes because they don't have children as well. Right? So there's 5. There's A, B, C, the 2 here, and then Z, according to the labels, right? Okay. Other things you should know. So there's this idea of a height, which we talked about when we were talking about heaps, but a height of a tree is just the number of edges along the longest path from the root to the leaf. It's also the number of levels in a tree if you index from 0. So let me just make that absolutely clear, because I think that can be confusing for a lot of you. If we have one level here, the level that the root is at, that's level 0. Then if we have the level that X and Y are at, that's level 1. The level that 1, 2, and 3 are at, that's level 2. And then the level that A, B, and C, and Z are, that's level 3. Since we have level 3 here, then the height here can be considered to be 3. And the less confusing way to see this is the fact that if we go from the root to the leaf and we just look at the longest path from the root to the leaf, we have 3 edges here that we have to traverse in order to get from the root to the leaf, right? So don't get this confused, but the height is in many ways just defined as the number of hops from the root to the leaf of the longest path from the root to the leaf. There can't be any cycles in a tree, yes. If you don't know what a cycle is, don't worry, we'll talk about it later. But for those of you who understand graphs, trees are acyclic graphs. Other things you should know, there's this idea of a subtree. So a subtree is just a fancy way of saying a tree within the main tree, and it cannot be the tree itself. So in other words, I can say that this blue section here is a subtree, but that for example, if I circle this entire thing, by definition, it should not be a subtree of itself, right? This entire tree cannot be a subtree of itself. How about this? If I select this thing here, these 3 nodes, 2, 3, and Z, is this a subtree? I'll give you 5 seconds. No, we're getting some no's in chat. Yeah, it is not a subtree, because in order to be a subtree, you have to have a tree. So if I just select these 3 random nodes, they're not connected to each other in such a way that they are a tree. How about if I selected these nodes here? Is it like a proper subset? Yeah, mathematically speaking, a subtree by definition in this class will not contain the tree itself. You can think of it as a proper subset if you know it from math, yes. If you have Y and this number 3 here, is this a subtree? Someone asked, can a child node be a child for more than one parent in a tree? No, a child node can only have one parent in a tree. Go ahead and type in chat. Do you think what I've circled, highlighted here in purple, is this a tree or not? This is not a subtree. This cannot be a subtree because it does not have the child Z here. So this Z has to be included for this entire thing to be considered a subtree. All right. So again, a tree has to include all of the children for each node. If I just select this 2 parts, like you can see that it has a tree structure, but since we know that 3 has another element here, this element Z, we have to include that in order for this to be a proper subtree as defined in this class. Other classes might define it differently. Other professors might define it differently, but this is how we're going to define it. And again, I'll post by the end of this week a vocab sheet so that y'all feel comfortable with it. All right. Would the root x be a subtree as well? No, because as we said earlier, a tree, the main tree cannot be a tree of itself. So if we say here's the root and we collect all of its children, this cannot count as a subtree based on the rule that we've put on the bottom here, right? These are semi-arbitrary definitions, but that's just to make it so that we're talking about the same thing in class, and that you don't get confused if you read other things on the internet. If I just have this node, is it a subtree? Yes or no? What do you think? This is a subtree, right? This actually counts as a subtree because it has no children, so we don't have to worry about capturing any of the other nodes underneath it. So a leaf on its own is always a subtree of the big tree, unless there's only a single node in the tree, in which case it's not. Okay, moving on. Let's take a look at the example here. We have this tree here, and we're going to try to answer all of these questions here. Right, I'll give you 10 seconds for the first question. What's the root of this tree? Okay, we're getting a bunch of 2s in chat. Everyone's just typing in 2, so I can just select this, right? This is the root. Is this what we're talking about? Right? Some of you are noticing that we should probably specify more that it's this 2 that we're talking about, right? The 2 that's on the top here. And that's important because if you notice that if we have the values don't have to be distinct in trees. We can have multiple nodes with 2 inside. So whenever we're saying what the root is, we're going to have to be a little bit more specific. So we have to say the node with 2 in it is the top node is the root, right? How many children does this node have? How many children does this tree have if it's rooted at the top node here? Do we establish height by numbers? Like, could we say height 0 or something? Sort of. So we could say levels, but whenever there's ambiguity on a question or something, I will try my best to make it unambiguous. We'll give you little labels or something so that you can identify which elements that you're actually talking about. That's a really good question. Definitely, we will try to make things unambiguous. And if anything's ever ambiguous and we realize it, then you'll get maybe some extra credit. Not extra credit, but if it's our fault that we were ambiguous, then we'll grade differently. But how many children do we have here, given that we have the tree rooted at this node 2 here? Go ahead and type in chat if you have it. 9 children, huh? That's a lot of children. Some people are saying 2. Some people are saying 4. Now, a lot more people are saying 2. If we're talking about just this tree, we are going to get 2 because we're not talking about the grandchildren or the great-grandchildren. We're only talking about the nodes that are immediately direct descendants of this tree, right? So whenever I say children, I just mean the direct descendants, not everything else that the tree might have. So the children's children and the children's children's children, we don't count in that count. If I were asking you about the descendants, how many descendants does the root node have? Then the answer here would be 9, right? Similar question to what we had before. How many leaves do we have here? Go ahead and type in chat if you have it. 5, right? We have 1, 2, 3, 4, 5. These are the only nodes without any children. So we have 5 here. And then how many nodes does this entire tree have? What do I mean when I say nodes? How many of these circles do we have here? 10. Yes. So if we're just counting up the number of nodes total, well, there's 10 nodes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's not meant to be anything scary. The goal here is just to answer some basic vocab questions when it um, comes to the tree and tree vocab, right? Okay, we have 10 nodes. How many subtrees do we have? Go ahead and take a look. I'll give you 20 seconds. Don't type in chat yet. Just wait. How many subtrees do we have? All right, what do we have? My question is wrong. Which question is wrong? Wait, I'm confused. Why is my question wrong? Someone said my question is wrong. We got a bunch of different numbers here. The question about the root or the whole tree? I see. So whenever okay, I see the confusion. So here, someone's saying that, okay, this question was about just the root node. And then all of these other questions are about the overall tree. That is true in the sense that I am asking how many leaves does the entire tree have? And I think when the important thing to realize is that children here means the exact direct descendants of the exact tree we're looking at right now. So if this is the root of the tree, then we want the rest of the children, which would be here and here. But when we're asking about leaves or something like that, we will be specifically talking about the entirety of the tree. Using a word like it in a question can be very ambiguous. That's fair. I'm not here to trick you, honestly. I'm here to use vocabulary the way I feel comfortable talking about it and the way I think most experienced software engineers will be talking about it. I could ask how many leaves a specific node has. That's true. For example, if I asked if this is the root of the tree, then we would have 2 leaves. But by default, you should just assume that I'm talking about the entire tree, which in this case is here, which means that we have 5 leaves in this case, right? I think this is a good point, and the ambiguity of language is also, sometimes tricky. But I'm not meant to trick anyone here. We all know what we're talking about, but at the same time, there's different ways to phrase it, and I agree with you that this way can be ambiguous. So let's go ahead and take a look at how many subtrees we have. And so for subtrees, I mean, how many subtrees of this entire tree do we have? And the answer here is 9. Let me just show you how I count it up. So for example, this entire thing is a subtree. This entire thing is a subtree. I can't count this entire thing as a subtree, right? Because that would be a tree in itself cannot be a subtree of itself, which was the definition from previous. This can be a subtree, right? Because this is a valid tree with its 9 as a root and then 4 as its child. And then this 4 on its own can also be a subtree. Likewise, we'll have these as subtrees. And also, this part here, this triangle bit, will also be a subtree. And then lastly, we have the children of the node rooted at 6 will also be subtrees. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is where that came from, okay? So this is, again, just used here to help you get familiar with the vocab. I will post a more formal vocab sheet and some more formal examples so that you don't get lost. But I really need everyone to be speaking the same type of term, using the same terms in the same language as I am. Because I know that in other places, we might use different terms in other courses or other websites. Are subtrees a power set? Not quite. The power set definition doesn't quite extend cleanly into what, asking what the power set of a tree is. I guess you could ask that, but all combinations of elements would not necessarily produce a subtree. So for example, this isn't a subtree, even though it might be in the power set. Someone's asking a math question. You can ignore it if you like. Okay, so what is the height of this tree? Go ahead and type in chat. Okay, we have 3 here. So the height here is 3 because the number of hops we have to go from the longest path from root to leaf is 3 here, right? So in other words, there's level 0, level 1, level 2, level 3, which is why the height would be 3. And as a follow-up question, if I were to make a node here, let's say this node here, come out of this node with 2 in it now has a child here, would the height of the tree increase? Yes or no? No, right? Okay, that's good. But if I were to go and make the path here, if I were to make a node come out of this element, then the height would increase because then the longest path actually increases as well, right? Okay. So let's go ahead and take a look at representing trees in Java. So basically, we're about to see the tree node class. It has 2 private instance variables. We have value, which is a generic type t. It could be an integer, it could be a string, it could be a boolean. And it's going to have children, which will be a list of tree nodes of t, since we can have any number of children. So if we have 0 children, if we have 8 children, if we have 19 children, if we have 5 children, having a list allows us to keep track of all of our children, even if we have more or less, right? These are going to be private instance variables. So since they're private, we have to have getter methods, which is get value and get children. Now, I know some of you aren't feeling super familiar with Java and classes, and this might seem a little bit strange or out of place for you. Like you might not know exactly what this means when I say private instance variables, but do your best to follow along and get the overall idea of things. The most important thing is how do we actually make trees and how we actually use trees in order to get values and stuff, right? So we're going to go ahead and take a look at this tree here. It's defined as a tree class. And what we have is a value and children here. It's defined as instance variables or private variables here. Now, if we want to get the value and the children, we want to set it whenever we create a new tree, we would do this constructor here. For example, if we only wanted to set the value and no children, we would use this constructor because this constructor just creates an empty list for the child. If we want to create a tree that has children, we would have, in this case, 2 arguments, a value and apparently a variable named chicken. And the reason why I put chicken here was just to illustrate that this children variable and this value variable are different from the variables that get passed in to tree node when we look at it as a constructor. But we set the value and the children accordingly, and then we get it out using the method get value and get children here. We also have this helper function called isLeaf, which just helps us out whenever something's a leaf, right? I'm going to go ahead and just show you some trees that we can represent. So for example, this tree here is a tree that has a root node with 5 in it. Right, so if we wanted a root node to have 5 in it, we definitely can. What is the T in the class? So T is a placeholder here that represents the type that we will have of our value. So for example, if we wanted to have a tree filled with strings as each of the values, then that T will become string. And the T gets filled in whenever you declare an actual tree. So this says, make me a tree node of integers called example. And the integer will be what T is here. All right, that's a great question. So T's are just, the T here is a feature in Java called a generic. And so if you want to learn more about that, you can type in generic Java. And you can learn more about generics. It's just a way to have a placeholder type whenever you want a data structure to hold different types of variables. So if you want a tree filled with integers or a tree filled with numbers, you can specify that accordingly. All right, great question. I'm going to move on. So in this case, we have a node that has 5 in it, and we're going to have a bunch of children to this 5. So you can see that we have arrays.as list, which just stores all of the children we care about. We're going to have a child here that gives me a single node rooted at 4, but it also has some children. So I guess what I mean is we have this as a tree in itself. That has the number 4 inside. And it's a child of 5 here. So we see that this node with 5 in it has a node with 4 in it. And this node with 4 in it is going to have some other nodes. It's going to have a node with 2 in it. Sorry, minus 1 in it here. And then we also have a node with 3 as well. All right. Okay. So in order to keep going, we're going to look at all the other children of 5. So this node with 5 in it actually has more children. Every element inside of this list is a child of the node with 5 in it. And some of these elements are more involved, right? So if we look here, we have another 3 nodes here. The next node here has a number 1. The node after has a number 0, and none of these have children, right? You can see that there's no second argument here. So we just assume that there's an empty list as the children because that's what the tree Java class defined here, right? We use this constructor. And in order to get the actual last element, we have a minus 3. And this has a lot more children, right? So we have to write this all out. So it has 3 children as well. It has a child with the root node of 5, a child with the root node value at the root node, which is 7, and a child whose value is 3, right? So we do write out all of these, and we point arrows here, right? So in this case, we know that there's a 5 as the first child in the first node. We have a 7 in the second node, and we have a 3 in the third node here. And lastly, the 5 itself has some children. How many children does 5 have, by the way, based on this code, if you're reading it? How many children will it have? Go ahead and type in chat. 1, 2, 3, 4. Okay, everyone's typing in 1. So hopefully this isn't scary, but the idea here is there's only one argument to erase that as list, so it has 1 child, which means that we have here a child that dangles out, which is the number, it has the value 2 here. And then we have another element here that has the number 8, right? And that's the entire tree. That's what example is. All right. Quick question, if I wanted to get the 7 here, if I want to get the 7 number, what would I have to type into the Java? Like, what would I have to type in here in order to get the 7? Example dot what in order to get the 7? I'll give you about 10 seconds, and then we'll work on it together. I'm just curious how many of you will figure this out based on what we've talked about. Okay, what do I have to type here in order to get the 7? Okay, we're getting a lot of question marks. All right. Dang, I didn't cover this in the other sections, so we're going to have to review that next lecture. All right, cool. So remember, the 2 methods we have are get value and get children. That's all we have, right? So in this case, we have to type get children, which will, if we just print this out, we'll get is a list filled with, 1 second, let me comment a few things out so that you don't get confused here. Please compile. If we just said example.get children, Why isn't this loading? Let me try refreshing. Yeah, maybe my strange. Okay. Let me just go ahead and it doesn't know either. Oh, that would be unlucky if that were the case. Oh no, what happened? Oh my. Hold on, let me try running it and see if it still works. There we go. All right, cool. Everything is fine. Okay, we get a list of 4 elements here. If you look at this, it's actually a list of 4 elements. This first tree node, this second tree node, this third tree node, this fourth tree node, okay? Yeah, those of you who understand that reference, welcome. Everything is okay. Everything is fine. In order to figure this out from there, we have to actually do get of 3, which will give us the exact tree node we care about, which is this one here, right? So if we had 4, that represented the 4 that we had here. 1, 2, 3, 4. And then the tree node on the very last end bit, we get by saying get of 3. From there, in order to get even more elements, we're going to have to do a call to get children again in order to get all of the children of this node with -3 in it. So this 5, this 7, this 3. And that will give us, hopefully, a list with 3 elements inside, right? To represent the 5, the 7, and the 3. And if you look, and if this doesn't crash on me, you can see there are 3 elements here accordingly, right? So everything makes sense so far. Give me a 3 in chat if you're feeling good about this. Hopefully this is making more sense. Nice. Yeah, so from here, we want to get the third element of the third child here, right? The last child here will actually, sorry, the second to last child here, which will give us the 7. So we'll actually have to type in get of 1 because this is 0 index. So this is the 0th child. This is the first child. And from there, we'll get another tree node, right? You can see this is recursive. Every time we call .get, we get a tree node. Every time we call get children, we get a list of tree nodes. So in this case, we get another tree node. And it's only after you click that value or get value here, do you finally actually properly get an integer, in this case, the 7, all right? So hopefully this makes sense. If it doesn't, go ahead and let me know in chat. Ask any questions you need in order to understand what's going on. The goal here is for you to feel comfortable with the syntax and how we represent trees. You can see here that if we want to get the 5, for example, we could just say system.out.println of example.get value, and that would give us the 5. Is the get value code built in? Yeah, it's right here. It's defined in tree.java, which will be given to you. All right. So let's go ahead and take a 5-minute break. We'll stop here, and then we'll come back afterwards to go and talk more about trees and tree methods. So if you are feeling good about the definition of trees, then the next thing you should try to do is take a look at this and try to convert this into an actual tree. So this is the type of question I might ask on a quiz later on. Yeah, my cat is being very loud today. I'm not sure why. I think he got fed a little bit earlier, so now his biological clock is demanding that he gets fed now instead of the normal time where he whines, which is like an hour from now. How's Nico doing? Well, he's energetic, as you can hear. Feed the boy? No, anyone who owns a cat knows you never feed the cat early. Can we represent the tree using left and right instead of get children and get? No, you can't. This is a tree with more variable children. You can have 0 children. You can have 8 children. Get left and get right are for binary trees, which we'll talk about next lecture. Um, I don't think Nico likes being on camera. The last section got to see Nico for a little bit, but I think Nico right now would probably bite and scratch at me if I tried to pick him up and get him here. Get children returns a list of children starting from left to right. Yeah. So the leftmost element is index 0. That's correct. And we're still on break here. You'll have 4 minutes left. Let's just all take a breather. Go to the bathroom if you need, get some water. You're all asking really good questions, by the way, so please do keep asking them if you need. Nico, hello. I have a cat. I have acquired cat. Can you see the cat? Ow. Can you see the cat if the camera is sharing screen right now? Or do you want it to be bigger? Okay, okay. Bye, Nico. Ah, this is why I warned him. I warned y'all he would bite if I picked him up, and it happened. Nico does not want to be picked up right now. I'm sorry, Nico. You don't get to eat yet. It's not time. I know you're hungry, but you're actually quite fat and well fed. There's no need for you to eat early. All right, we got 2 more minutes of break, and then we'll go back into it. The cat bit and scratched me, and now he's looking all innocent, asking for food. All right. So now we're going to go ahead and take a look at writing functions on trees, right? So the goal here is to understand how we actually write methods on trees, the same way that we would write methods on lists or arrays or anything like that. Go ahead and type in some tree if you're back and you're ready to learn. And we'll get started right after that. Nice. Okay, so some tree here will take in a tree of integers, and it's going to return all of the different numbers inside, added all up. So in this case, we have all of these numbers inside of this tree. If we add them all together, it would output 61. So the goal here is to be able to write that function. And I'll just go ahead and walk through it step by step, because I think it's valuable to see an example before we go and try to tackle it together. And you can see here that I've already written the code. The expectation here is that we have let me write it differently. If I were to write this from scratch, how would we actually approach this, right? What's the goal and what's the way to actually write this out? Well, the goal is to write some tree. The approach is to use recursion. You know that recursion, by definition, will provide you a way to traverse items, right? You can use recursion to traverse various things. And we know that the tree in itself is a recursive data structure. So we want to make sure that we have a similar approach when we're solving problems here. We can use recursion to traverse the tree and be able to actually look at every single element and sum it all up because of the recursive nature of the tree. So if we want to use recursion, that means we have to have base cases, recursive cases, and a recursive step, and then a combination step, right? A way to kind of sum everything up afterwards. And so one way to think about this is, okay, in order to figure out the base cases, what's the simplest type of tree that I could take in as input in order to actually get a value out? Go ahead and type in chat. What do you think is the simplest kind of tree that we would have? A tree with no children, right? So a leaf. So in this case, if the tree is a leaf, then all you want to do is to grab the value at that tree and output it, right? So what we would want to do is return the value. Otherwise, there's going to be a step where we actually have to add up all of the rest of the tree. So we want to call sum tree on each child, right? Because each child is going to be in itself a tree. So for example, we want to call sum tree. We want to call sum tree on this child. We want to call sum tree on this child. We want to call sum tree on this child. We want to call sum tree on this child, right? And that will give us a bunch of numbers, right? If we call sum tree on the first child, we would have 4 plus 3 plus minus 1 gives us 6, right? That would be the result of calling sum tree here. Calling sum tree on here will just give us the 1. Calling sum tree here should just give us the 0. Calling sum tree here should give us, in this case, 22. And the key here is to assume, once you have a smaller argument, that you can assume that sum tree will just magically work for the current smaller argument, right? So given a smaller tree, if I call sum tree on it, I'm just going to pretend like it will be guaranteed to give me the right result. That's how we should think about writing recursive functions, especially ones on trees, right? So we just assume that we can go ahead and get all of these numbers back that are the results of calling sum tree from all of the different values, all of the different children, right? Give me a yes in chat if you understand that argument of where the recursive step comes from, and give me a question mark if you're confused why we're doing this, right? We know we want to call sum tree on all of these children, right? Because that is how recursion works. We don't know exactly what the function will look like, but the hope is that we will be able to sum up all the values at the end of the day, right? So again, we want to pretend like sum tree is already written so that when we call sum tree on a smaller argument, we just pretend, oh, it gives us the right answer. We don't have to like think exactly about all the recursive calls that get made. Instead, we're going to think of it in a more abstract way. So we call sum tree on each child. It's going to give us all of these values. What is the combination step? Like, what do we have to do with all of these numbers? And is there anything else we're missing for the combination step? So since we know we call sum tree on each child, that's like one thing. But how about, what's the rest of it look like? How do we actually do that? Go ahead and type in chat if you have an idea. Someone already typed in an idea. It's a pretty good idea. What other ideas do we have? Okay. Add up all the sums from the calls to sum tree above, and also add the value of the current tree, right? So someone said add the parent. Basically, you want to go and say, okay, we got the 6, right? We add it with the 1 and we get 7. We add it with the 0, we still have 7. We add it with the 22 and we get 29. Now that's not the end of it because there's this 5 here that we want to add as well. So we want to add the 5 in as well. Okay. So the goal is to take all of the numbers, add them together, and also add the 5, which will in this case give us 34 as the sum of the tree. Right, so the expectation is that we're going to add all these numbers together that we get back from calling sum tree a bunch. And then we're going to also add them to the number 5 here so that we can go ahead and, excuse me, go ahead and make that work. So how do we actually translate this to code? I'll just go and type it out. So we'll check to see if the current tree is a leaf. then we're going to return tree that get value, right? So if it's just the, let's say a node with 5 in it, just the node with 5 in it, this thing in red here, and not anything else, then we just want to return the 5, right? That's our base case. Otherwise, we want to say our sum is going to be equal to just the current value, and then we're going to go and iterate through all the children. We got to get all the children. And here's how we do it. Tree node of integer child colon tree that get children here. All right, we saw before that get children gives us a list of trees, which means this syntax here will iterate through every single element in the tree. From there, we can say sum plus equals the sum tree of child, which takes in, remember, a child is a tree node. So if we call sum tree on a smaller node, that's how what we're actually doing here. And we're adding up all the numbers up from the previous elements here, right? It first starts out as tree.getValue, and then we'll add up every single sum tree element from there. So every child we'll call sum tree on it, and then we'll go ahead and add that to the sum. And then after we're done with all of the children, we return the sum at the end, right? So if we went and tested this out, by commenting in line 59, and just run it, we should see a 34 come out, okay? Type in 34 if you feel like you understand how sum tree works. Okay, people are feeling good about this in theory. All right, so here's the test. If you actually understand how this works, what happens if I replace sum instead of saying tree.value? I change this to 0. All right? I'll give you 20 seconds. If you really understand the algorithm, what happens if we change the tree.getValue to a 0 instead? Someone's asking, okay, what happens, like, how can you explain this a little bit in more detail? This colon just allows us to iterate through every single element in the list of children. So this will give me the list of all the children, right? So it will give me, in a list, this thing, this thing, this thing, and this thing. In this syntax here, just says child will start off being this thing, and then it'll be this thing, and then it'll be this thing, and then it'll be this thing. Right? So that syntax with the colon just allows us to iterate through every single child independently and do something to that child. Okay, type in chat. What do you think the answer should be if I have this here? Okay, some people are saying 0. Some people are saying it'll break. Some people are saying 29. Some people are confused. A lot of people are typing in 0. Let's go ahead and hit run. We got 21 here, right? So here we notice that 21 comes from actually adding up all of the leaves. Some of you called it. It's adding up all of these values here, right? 10 plus 8 is 18, plus 1 is 19, plus 3 is 22, minus 1 is 21. That's where this comes from, right? So what we are saying is that by removing the tree.getValue here, we are no longer keeping track of every single element on the inside of the tree. The value of every parent gets ignored in this case, right? And we don't want that. So that's why we put the tree.getValue back if we're trying to sum up all the elements in the tree. Okay. What happens if I said sum of tree equals tree.getValue plus sum of tree of child in the for loop? If we went and said, if we said this, if we run this, we get 5 because the value of the for loop does get added multiple times, but we just replace the value of sum each time, which means that if we call here, what we'll do is we'll call sum tree on the right-hand side here, and the sum will cancel out anyways, and then we'll just have the 5, which is where this 5 comes from. Okay, so let's move on and try to tackle another problem. Let's go ahead and try to tackle max of tree. So max of tree takes in a tree of integers and returns the maximum value, which is why when we take in this tree, we're going to go ahead and output 11. 11 is going to be the biggest value in all of these elements here. So if we go back to our example and we try to write max of tree, I wrote it earlier, but I'm going to go ahead and do it again from scratch. Actually, before we go and look at max of tree, I have a question for you. If I take out the base case here, what do you think will happen? Let's go ahead and do a quick check. All right. First option. Everything is normal. We get the correct answer. Second option, different answer. Third option, errors, like it doesn't compile. Fourth option, it crashes. All right. Go ahead and type in chat. What do you think the answer is here if I remove the base case for some tree? I just nuked the base case for some tree. Will we get the right answer? Will it crash? Will it give us a syntax or compilation error? Or will it give us a different answer altogether? Okay, we're getting a bunch of different answers here, which is really interesting. Okay, let me run this. We run it. We get 5 because there's still a bug from before. Oh, sorry. I meant for this to be back to what it said before. Ignore this. Okay, so let's run it. Everyone says it crashes. As you can see, it did not crash. It returned, the answer here was A. We got the same answer as before, right? And let's just think about why this works, why this is actually working. If we look and we try this, right? If we take this here and we just pass in a 5 here as argument, let's say we pass in the tree with 5 in it into sum tree. The first thing we're going to do is say sum is going to be equal to 5, right? That's not confusing. Sum is equal to 5. And we know that get children is going to return an empty list. Since get children will return an empty list, the for loop doesn't fire. Since the for loop doesn't fire, we just go ahead and return sum, which is 5, and then we're done, right? So if it works on this tree, on this small tree here, then when we recurse down on the bigger tree, the same properties will hold. Every time we see a leaf, we'll process it properly because we just don't go into the for loop. We never make any recursive calls on the leaf, right? Someone asked, would it work on an empty tree? I don't know, because there are no empty trees in this lecture. There's no such thing as an empty tree in this version of trees. Remember, this tree can have variable amounts of children, and there's no such thing as a null tree. We'll see in the next lecture this idea of a binary tree, which of course will have null trees. But in this case, we do not, all right? So that's a great question. Make sure you are all feeling good about that. Some tree doesn't include the root. It does. We say tree.getValue, and that's how we get the root value. I added up all the numbers and it's 39. Wait, hold on. I'm pretty sure this is 34. This is 10, 12, and this was 22, I think, right? This is 10, 22. Yeah, so this is 22. This was, what did I just say? 10 plus 12? 12 plus 22 is 34. This is how math works, I think. I'm pretty sure there's a part, maybe my handwriting is bad, but these all these numbers should sum up to 34. You can check out the copy. I'll give you a copy of this in chat in case you want to play around with it. Because the next thing we're going to do is actually write max of tree. All right, so we checked out sum tree, which was, relatively straightforward, hopefully. We're going to do max tree now, which will hopefully also be relatively straightforward. And we're going to code in the same way as we did before, right? We're going to go ahead and try out writing this out with a base case and some recursive cases and a way to combine all the answers. So what I want you to do is take the next minute to think about what are the base cases for max of tree? What are the recursive steps? And then what is the combination step? And how would we write this out? You have 1 minute, and we'll go over it afterwards. We're looking for the max value. So if we had the max value here, we should output 8. Okay, I'll give you another 10 seconds. And when you're ready, what is the base case? How do we check the base case here? Go ahead and type in chat if you have it. What do we consider the base case here? Remember, a base case is the most straightforward or smallest argument you could pass in, right? So what you should expect is, well, the simplest tree I can imagine is a tree with just one node and nothing else. So a leaf, right? So we do a similar check. So if leaf return value, right? If there's only a node with 6 in it, I just want to return the 6. That's the biggest node value that I have inside of the tree. Otherwise, I'm going to call max of tree on all children. Right? And the combination step, what do you think the combination step looks like here? How do we actually use this? If we have a max tree for each child, that means that at every step here, we're going to take max of tree and we're going to get the biggest number from it. So in this case, it'd be 4 for this one. In this case, it'd just be 1. In this case, it'd be 0. In this case, it would be 8, right? Because that's the biggest node in this tree. If that's the case, then what we want is to take the max of all of these values and also the max of this here, right? We compare 5 and 4. 5 wins out, so that's going to be the max. We compare 5 and 1. 5's going to win out, so that's going to be the max. We compare 5 and 0. 5's still the biggest one, so we compare, and that's the max. And then we compare 5 and 8. 8's finally bigger, so we return 8 at the end, right? So we need some idea or concept of keeping track of the max number we've seen so far so that we can go ahead and take the max, right? So take the max of all of the current value as well as the max of tree of all the children, right? So what that looks like in practice is we'll do this check. We'll say here, if the tree is a leaf, then we'll return the tree's value. Otherwise, we're going to iterate through every single element here. I'm sorry for all of you who own cats and who are getting whose cats are upset that my cat is so loud. I'm hearing that from multiple people in this and it's kind of hilarious, but also I feel bad. All right. So we iterate through each child. We're gonna say first we have a max so far, the integer max so far, which is equal to tree.getValue. Do we need the base case? No, I'm going to delete it afterwards, but I'm showing you the base case just so that you understand and everyone can follow along, right? Implicit, like we never need, sorry, let me make that clear. In these examples, we don't need an explicit base case. We'll remove it and it'll still be fine, but I'm including it for the sake of people learning. So in this case, max so far is going to be equal to the max of the current max so far, as well as, well, let's try calling max on one of the children. And then at the end, we'll return the max so far. So if this works, then if we call max of tree here, we should get 8. So let's try running it and see what happens. We should get an 8 here. And we do. Cool. So again, the way this works is that we're going to go ahead and check to see if 5 is a leaf. And it's not. So we're going to go ahead and say, okay, we have a max so far. And that's going to equal 5 at the beginning because it's equal to the tree's current value, which is 5. Otherwise, and then we're going to iterate through all of the children and call max so far on each of them. So for example, max so far on this one, as I said before, will return 4. If it returns 4, then we're going to compare the 4 against the 5 by calling math.max and say, okay, whatever is the biggest, that's what max so far is afterwards. So in this case, the 5 stays a 5, right? The max here is still 5. Then we do it for this child here. We call max of tree on this child. Max of tree on this child is going to return 1. We're going to compare it against the max so far, which is still 5. And since it's 5, then all we have to do is to output the bigger of those two numbers. 5 is still bigger, right? So nothing really changes. Do it one more time for this child. Compare 0 and 5. It still stays the same. And then lastly, if we call max of tree on this one, then we'll get an 8 because we just trust that max of tree will work on this smaller tree. And when we compare 8 against 5, the 8 wins out. So max of so far is actually finally equal to 8. And then we return here. Okay? And as we said before, we can delete this base case and nothing will change. We will still get the right answer because the base case will be handled by the fact that we captured the tree's value here and we'll return it and we'll skip the recursive calls if the children right now is an empty list. Okay? All right, so let's go ahead and take another break. We'll take a 5-minute break and then we'll come back and take a look at printing trees, right? If you have any questions and concerns, feel free to ask. And I will go, maybe I'll feed my cat. I'm not sure. We'll find out soon. But let's take a 5-minute break from here. If you have any questions, let me know. Okay, I have fed my cat. Hopefully he will be more happy now. By the way, if you ever feel annoyed that my cat is meowing really hard, please let me know and I'll be happy to like adjust the schedule. Right now, from what I understand in chat, you hear him, but it's not like too distracting. If it's distracting, let me know and I'll like do something about it. We have a schedule that we're trying to keep to, and normally he expects to be fed like in the middle of this lecture. Wow, cat greater than class. I don't know if I agree with that, but my cat is certainly needy sometimes. Okay, we got like another 2 minutes and then we'll go ahead and dive into the last portion of the class, which is on printing elements. Yeah, he's busy eating, which is why it's quiet right now. He's very loud. Like you can hear him on microphone. This is a microphone that only points this direction and you can still hear him. Which is why sometimes when I'm lecturing, it seems like I'm distracted because I'm trying to explain things while a cat is like at full blast and I'm like right next to him. But hopefully my explanation still, for the most part, makes sense and y'all are following along. A sound wall? Well, I don't have the space. My apartment is rather small. And generally speaking, if he doesn't bother me, then he'll bother my girlfriend, and my girlfriend is also working at the same time. So it's a lose-lose proposition. Like ignoring the cat, I guess, is okay, but then he'll get into trouble. I'm getting a lot of support for Nico in the in the chat here. What is my typing speed? I don't know, probably slightly bigger, slightly faster than 100. I was thinking in future we might play like type racer in chat, but maybe not. I'd probably get beat by some of you. I know some of you are very fast typers. Yeah, I'm using QWERTY. I'm not using anything fancy. All right. I mean, I'm just using a normal keyboard. This is a this is a normal keyboard. It's actually kind of loud because of the blue switches. I might switch back to my previous keyboard. All right, let's go ahead and get started. Everyone, we're going to talk about printing trees now. So in other words, we're going to talk about printing elements in trees. And in order to print elements in trees, there's two things we need to know. Goal, print elements in trees. And then we're going to need to review queues and stacks. But before that, we're gonna go and try to type in print tree even before we look at the queues and stacks. So let's take a look at print tree down here, which if you look at it, it's like 4 lines, right? I'm going to show you what print tree does, or I'm going to talk to you about what print tree does, and then we're going to go ahead and take a look at how it actually does that. So what we'll do is see that we'll print out the current value, and then we're going to look at all of the children, and we're going to print out their value too by recursively calling print tree. So if we go and actually try this out, so let's say we call print tree of 3. We want to see how we're actually printing out, what the ordering of print tree it will do based on this code. All right. So I'm going to walk through this. We're going to walk through this together and see if we can understand what's going on. First thing we'll do is we'll print out 5 because that's what the code tells us to do, right? Type 5 in chat if you're ready to go and walk through this with me. We're looking at print tree, which will just print out all the elements in the tree. And we know that at the beginning, we're going to print out 5. And then from there, we will go ahead and check the children and call print tree on all of the children. So the first thing we'll do is we'll call print tree on this child here, right? What's the first number that comes out of printing tree here? Like if we call print tree on this child, what's the first number that will come out? We should get 4, right? Because that's the value at the current child, right? We're just doing this algorithm again, but now on the smaller tree. We get 4 out here. So if we get 4 and that gets printed out, then we go and call print tree on all of its children, in which case the first child we examine is this -1. And following the same pattern, we'll print out -1. And since it doesn't have any children to print out further, we'll stop here, go back to the world where we were doing print tree of the node with 4 in it, and then look at its second child. And we'll print out the 3 here. Right? So far we've printed out everything on this child's side, like this child here. We've printed out all the elements here. So we'll just go ahead and look at the next child that gets printed out. In this case, we'll get a 1, right? And it has no children, so we'll just stop and move on to the next child of 5. In this case, we'll get 0. And then lastly, we'll look at the last child of 5, which is this entire mess. And the first thing we'll do is we'll, again, print out the value at this child, right? We're treating this as the tree now when we call print tree of this entire thing. So we get the the -3 to come out first. And then we'll call print tree on all of its children. So we first call print tree on this left child here, which is why we'll get 5, and then 2, and then 8, right? Based on this pattern that we have. Then we'll move on to the second child of -3, and we get this 7. And lastly, the 3 at the end. So the traversal order is going from left to right. And then we're also looking at the elements in such a way that we are going path by path, or in other words, depth first, right? As someone in chat is typing. The idea is that we're looking at the elements by going through and checking out every single path and going as deep as possible. And then we'll come back and then look at this element, and then we'll come back and then we'll look at this element. We'll come back and we'll look at this element, come back and look at this element, and then go as deep as possible down here. And then we'll come back and then look at this element, and then come back and then look at this element here, right? I'll just run it so you can see that this does what I say it does. We get the same ordering here: 5, 4, -1, 3, 1, 0, -3, 5, 2, 8, 7, 3. Okay. Now, if we go on and check out this slide, what we want to do is try to print out in different ways. So not only are we just going to print out elements in the tree, we're going to print them out in different orders. And in order to do that, we have to rely on data structures instead of recursion. So we're going to use data structures such as queues and stacks. Queues are first in, first out, and stacks are last in, first out. So hopefully this seems familiar, because it should be something that you remember from 2720. In other words, if we have a queue, the input for a queue is that we'll have whatever we put into a queue, the first thing that comes in is the first thing that'll go out. So if the input here was 1 and then 2 and then 3 and then 4, then the output should also be 1, 2, 3, and 4, right? And someone just put in a very helpful analogy in the chat. So like, for example, if you're waiting in line for ice cream, the first person who is in line is the first person that gets served, right? That's what first in, first out means here. Now, if you're talking about stacks, that's different. We're thinking about maybe a deck of cards or thinking about a stack of plates. If I put all of the plates into a stack, the last element I put on the stack will be the first one I take out. The first plate I take off the stack was the last one I put on, right? So the input will be 1, 2, 3, and 4, but the output will be the last element that we put in first, which is 4, followed by 3, 2, and then 1, okay? And why do we care about this? Well, the entire goal is to try to print trees out in specific orders. We'll print the elements of the trees out using a stack and a queue, and we'll find out that they have different orderings in order to make that happen. If we use a queue, we're going to do it level by level. In other words, breadth first. And if we use a stack, we're going to do path by path. In other words, depth first. If we do breadth first, what we want, for example, here, is to just print out all the elements from left to right and top to bottom. Or top to bottom, left to right. So we print out the 2 first. And then we'll print out the 5 and the 7 and the 5 in order. And then the 2, the 10, the 6, the 9, everything in order here. And then the 5, the 11, and the 4, right? So you can see here that there's almost like a cadence where we print out everything on the first level, everything on the second level, everything on the third level, and everything on the fourth level. Or level 0, everything on level 0, everything on level 1, everything on level 2, everything on level 3, from left to right. Okay, so if we were to look at the example in here, I'll give you maybe 30 seconds to try to figure this out. What is the ordering here if we want to print this out? Someone is asking, this takes longer than the first way. Well, the runtime will actually be the same, but we haven't talked about runtime yet. But we'll cover that next lecture. But for now, let's just think about this. What is in here going to be the ordering if we want to do this breadth first? So again, you should be typing in chat, but not hitting enter, what the ordering of these elements should all be. Okay, go ahead and type in chat if you have it. So we'll have the 5 first, followed by the 4, the 1, the 0, the -3, the -1, the 3, the 5, the 7, the 3, the 2, the 8. Yeah, nice. Hopefully that's not too scary. And we're going to go ahead and see a code that allows us to do that. So print tree 2 does that ordering of print. Like we're printing out all the elements from top to bottom and left to right. And the way we'll do this is we'll start by creating a queue. So we call this, if you look here, Java uses this syntax in order to create a queue. We say queue, open square, open brace, tree node, integer, close, right? So these are, I guess, caret braces. And we call it queue because I'm unimaginative, and this is an example in lecture. And we say that it's a linked list. So a linked list actually can be used as a queue if we want to. We're going to add in the tree first. And the tree here will basically be at the very beginning. This element here, just the node with 5 in it. right? So when I write this, what I really mean is that this thing here represents this entire tree. All right. So this entire tree is represented as node of 5. And we're going to go and try to process it based on this code here. All right. Type in 5 in chat if you understand what we've done so far. We've done everything up until line 107. And all we've done is taken this tree and thrown it into a queue. Cool. We're going to check and say, while the queue is not empty, which is what 108 means, we're going to pop out an element. And then we're going to print out the current value and then add all of its children. So doing that in order means that we first pop out the 5. The tree here gets removed from the queue. And then we're going to print out the value, which is 5. And then we're going to add all of its children. So we'll add the node with 4 in it, which was its first child, the node with 1 in it afterwards, and then the node with 0 in it, and then the node with -3 in it, right? Now, again, each of these represent the corresponding children in the tree. I just don't want to try to draw them physically into the queue. It takes too long. So we know that this entire thing is the first argument here. This entire thing is the second argument. This is the third, and this is the fourth, right? So since this is a queue, the first thing we inserted is the first thing that we remove. So we remove right now that we've added 4 things at once, we remove the node with 4 in it. We print it out. We print out the value at that node, and then we add all of its children. Now, here's the first question that I want to ask here. Since we're using a queue, when we add the node with -1 in it and the node with 3 in it, will we add to the beginning, to the left here, or to the right? Go ahead and type in chat. What do you think, left or right? We're adding to the end, right? Because again, this is working exactly like a line would be at an ice cream shop. The first one that we added will be the first process. So if we're adding more nodes, we have to add them to the end of the line, just like how all lines work, right? So in this case, we'll add node -1 and node 3 at the end, and then we'll just go ahead and process the next element. In this case, we'll process node of 1, right? No skipping, exactly. So we'll process this node, we'll print it out, and it has no children, so we don't add anything into the queue. Then we'll do the same thing for 0. 0, we remove it from the queue, we add it here, right? We print it out, and then we add all of its children, but it doesn't have any children. And then we check to see, hey, is the queue still have elements? It does, so we go and look at the next element here, right? We look at this node with -3. We print out the -3. We add all of its children. So this will be node of 5, node of 7, and node of 3. Okay? Because we're going from left to right when we examine the children, and we add them all in one step at a time. Lastly, we will add in, we'll process the node with -1 in it, right? Because we're trying to go and in order. So that's the next node in my queue. So we'll print out -1. It doesn't have any children, so we keep going. Node with 3 in it, same logic. The node with 5 in it, this has children. So once we remove it and then print it out, we have to go ahead and call or add all of its children, which in this case is just the node with 2 in it. From there, we'll go ahead and keep going. Remove the 7, print the 7, no children from 7, so we keep going. Remove the 3, node with 3 in it, print the 3, and then we add any children. It doesn't have any, so we keep going. We remove the 2, we print the 2, we add the children, in this case, the node with 8 in it, and then we remove the 8, print the 8, add its children, and then we're finally done. All right, so let's see this in action. This is the wrong call, so let me fix that. Okay, so we got the exact same ordering that we expected, right? So that was level by level or breadth first search. And we use the queue that we put elements in, and then we processed its children, right? We put one element in, we removed it, we processed it, and then we added all of its children in here. Okay. So let's go ahead and look at another version of this. So I accidentally highlighted print tree 3 because it has exactly the same structure as print tree 2, right? We add the initial root element into the queue, and then we check to see while the queue is not empty, we're going to remove the first element from the queue. We're going to go ahead and print out the value at that element, and then we're going to add all of its children. Print tree 3 does something very similar, except it uses a stack. Now, a stack is last in, first out. So if you remember, think of a stack of plates or a deck of cards. The first card I put on top will be the last card I remove from a stack of cards, a deck of cards, or the first plate I put in to a stack of plates will be the last one I remove out, assuming I'm removing from the top here. So likewise, the only things that change here, I made the while loop, the for loop more explicit. And if we have time, we won't have time, so we'll talk about that later. But basically, we have a tree that gets pushed in instead of added in. And whenever we remove, we say pop instead. And that's all there is. That's the biggest difference is we have the stack. We say stack here instead of queue. We use a stack instead of a linked list. And then we call push and then pop here, right? Like those are the only big differences here. I made a while loop a little bit more explicit, or sorry, the for loop a little bit more explicit, and that's for reasons we'll probably look at later. So if you understand how this works, if you feel comfortable with this, if you think you understand how this code works, what do you think will happen when I call print tree 3 on this tree? I'll give you 1 minute to think this out, and then we'll go through it together, right? Some of you are like, oh yeah, breadth first search, depth first search. I've done this forever. Like this is no problem. Okay, give me the right answer here. We'll see. I'll give you another 40 seconds to think this through. All right. What do you think? Go ahead and type it in chat. What do you think the output should be on this tree? Interesting. Very interesting. We're getting a bunch of different answers in chat. So section 2 earlier today got all the wrong answers, but their answers were a different kind of wrong than all the wrong answers I'm seeing here. Let's go ahead and hit play and see what happens. Assuming that my replit doesn't crash on me, which it might. Okay, we hit play here because we're calling print tree on the example, which is this tree. And what we get is 5, -3, 3, 7, 5, 2, 8, 0, 1, 4, 3, -1, right? So I was asking what happens when we call print tree on this tree using print tree 3. So print tree 3 does something slightly strange because it goes from right to left. It doesn't go from left to right, right? We went through the right side first, and a lot of your answers, it looked like went and looked here first, right? You thought we were going in this direction, in this order. And then you all got baited because what actually happened was we went from right to left. We started here and then went our way down, depth first still, but we went from right to left. So why or how did this happen, right? Like we need to figure this out. So let's go ahead and take a look by working through the example, and I'll move a little bit quicker now because we're short on time. We'll start with the stack S is equal to, we're looking at print tree 3, right? First thing we're going to do is we're going to add in node of 5 into our stack. All right, and then we're going to go ahead and say, while the stack's not empty, it currently isn't, we'll pop the element out, we'll print it out, and then we're going to add all of its children. Well, if we add all of its children, we're going to add from left to right, just like we said before, because that's what the code says. We go from index 0 all the way up to index size -1, and we'll add all of its children. So we'll add the 4, we'll add the 1, we'll add the 0, and we'll add the -1. Here's the kicker, though. Now that we've added all of the children, we go back and we check to see if the size of the list, the size of the stack is greater than 0. It is, so we keep going. What's the first element we remove here? Take 10 seconds. What is the first element we remove from the stack if we're doing last in, first out? Go ahead and type in chat. -1, right? The node that has -3 in it is the first element that gets removed because we're doing last in, first out. So in that case, we go ahead and we remove the -3, the node with -3. We print out the -3 itself, and we add all of its children, which in this case will be added to the right still and have node of 5 followed by node of 7 followed by node of 3. Okay? We keep going. We do the same process. We'll remove the 3, which was the last thing that we added, and we print it out. So this 3 got printed out next, which matches the output that we have. And then we'll process its children. It doesn't have any, so we'll move on to the next element, which is 7. 7 gets removed, 7 gets printed. It has no children. 5 gets removed because it's the next thing that we added, right? It was the latest thing that we added beyond everything else that we already removed. We'll add its children. So in this case, then we'll print 5 out, and then we'll add its children, which is the node with 2 in it. The node with 2 in it, we'll go ahead and remove it, print it, and then add its children, which is the node with 8 in it. The node with 8 in it, we'll remove it, print it, and then it has no children, so we move on. We process 0 and 1 the same way, so 0 gets printed out, 1 gets printed out. And lastly, we have 4. 4 gets printed out first, and then we process its children, so we add in the -1 into the stack, and then the node with 3 into the stack. From there, we process the 3 first, and then the -1 last, and then we're done, right? So the key here is to observe that stacks will actually print out path by path, but it'll actually go through in a different order. We're going to print out the 2 and then go down this direction, right? And here in this separate example, we're going and printing out here first, and then down here, and then here, and then here, and then here, right? So this ordering is still path by path and breadth first, but it's going from right to left. And that's because of the nature of the stack. We had a different order as a result. I wrote 8 instead of, I wrote 6 in place of 8. You are, wait, where's the 8? There is no 8 in here. I'm so confused. There should be a 3 here, though. That needs to be fixed. If you're talking about the previous example, I might have made a typo. Yeah, good call. Okay, we're going to move on because we're out of time. Let's go ahead and do takeaways. Thank you for correcting me, by the way. I really appreciate it. Trees are the recursive data structures that represent hierarchy. Don't confuse trees with binary trees or BSTs. You can write algorithms on trees by using recursion and iteration, and sometimes you have to use both. And there are several ways to traverse every single element of a tree. So we can do it recursively, which is depth first. We could do level by level using a queue. Or we could do path by path, which is, again, depth first, but it's using a stack, which gives us a different ordering. Quiz 4 is out this Wednesday and Thursday. So it covers divide and conquer, O-of-N sorting, and trees. And that's it. If you have any other questions, feel free to ask. Thank you so much for your time. And we're in office hours now. After this lecture is always office hours, so you can ask us any questions you'd like.